Okay. All right. Wow. Thanks for the applause. All right. Okay. Cool. So yeah. So I'll be talking about two courses. So the machine learning, and the second one is a more advanced course, a graduate level course on general models. So I'll talk about machine learning first. So obviously everybody has heard a lot about machine learning, right? And this course is basically about the fundamentals. Okay, what's going on here? 1 second. Okay, all right. Yeah, so I think maybe the cable or something. Okay. Everybody can hear me, right? Yes, okay, good. All right. I won't move around anymore. So yeah, so okay, why do we need machine learning, right? So suppose we want to write a Does it okay? Have to, I'm not sure. Okay. Hello, testing, 1, 2, 3. Let me see if oh, handout lapel. Let me actually try this. Oh, it doesn't work. It is working. Okay. Okay. All right. Sorry about that. Yeah. So okay. So suppose we want to write a program that can recognize shares, right? So you can try. I have no idea. Give me 1 second. Is there another site? Um, There's no other map. um, another, another. I see. Okay. Maybe let me just place it on the table. And I'll just, okay. Hopefully it doesn't happen anymore. Okay, so suppose we want to write a program that recognizes shares, right? So, you could actually try to write down rules, right, that would characterize, right, what a share would be. And, you make a first attempt. And, maybe you take a look and then you would say that a chair is something that has a seat, a back and four legs. You think that kind of captures the concept of chair, but then you run into another chair, right? And it doesn't quite fit the definition, right? So this chair doesn't really have the four legs. And then so, you may say something like a chair is something that has a seat, a back, and multiple legs. And you come across another chair and doesn't quite work either. And so, maybe you would say that a chair is something that has a seat, a back, and a frame. And that doesn't work, right? It doesn't have a frame now, so a chair is something that has a seat in the back, right? And then you come across another example, right? And well, I mean, maybe you finally come up with the following, right? You say that the chair is something that has a seat. And you think you're good, but then you come across another example, right? And this is not a chair. So the moral to the story is that there are exceptions to every rule and exceptions to every exception, right? And so that's why it's hard to actually write down a program, right, that can actually recognize something, as simple as the concept of a chair. Now, how do humans actually do it? We don't really know, right, the algorithm that our brain uses, right, to actually perform that recognition. But we can try to teach another human, right, using examples. And so that's really where the idea of machine learning comes from, right? So Alan Turing, back in the 50s, proposed this notion of a learning machine, which consists of a machine that simulates a child brain, right? And the analogy that he used was that it's a blank notebook, and all you specify is just the simple mechanism, right, that will allow you to read and write from that notebook. And then you would also have a way of teaching the child machine, right? And then so that should be, simple because intuitively we know how to teach a human child, right? And the way we do that, right, is to reward good behavior and penalize bad behavior, right? And so that's essentially the idea, right, that he came up with. And the important feature, he says, right, of a learning machine is that its teacher will often be very largely ignorant of what's going on inside, right? So even today, we don't really know how the brain actually works, right? But generations of teachers have successfully taught students, right? And this is like essentially the idea, right, behind machine learning. So in modern terms, the child machine, right, is known as a model. The blank sheets are known as model parameters, and the teacher is known as the loss function, right? And so here, essentially, in the picture, we have the simplest example, right, of a machine learning model, right, which is just linear regression. So you can see here that the inputs, right, would be what's on the x-axis. The outputs would be what's on the y-axis, right? And what you essentially try to do here, right, is to come up with a way of predicting the inputs, predicting the output from inputs, right, by looking at all the different observations, right, that you have. And from those examples, right, you will try to come up with a model, right, that gives you the right prediction. And the teacher is just going to say that given the model, right, how good or bad predictions are, right? So you ideally want to find something that minimizes the error, right, of the prediction. And that is measured by what's known as a loss function. So, right, so at the end of the day, right, after, we tried all the different kinds of models, right, we can essentially come up, right, with the best model, which in this case is the line of best fit, right? Now, what can machine learning do, right? So you can do lots of things, right? So really it underlies, right, pretty much, all of AI, right? So let's say, for example, in computer vision, right, you would like to predict, different aspects of the image, right? Maybe where the face is, right, in this example, or what kind of objects, right, something is. And in natural language processing, you want to answer the user's questions. Maybe you want some text. In robotics, you may want to predict, right, motor control, right, like actions that you may take, right? So, let's say in this case of self-driving car, right, where you want to go, right, and what the throttle is. And in traditional AI, right, you want to predict the next steps that you would do, right? So maybe, you want to place your chess piece somewhere, right? Or, what kind of piece you want to move. And so that's essentially what machine learning allows you to do. In the course, we're just going to be talking about the fundamentals of machine learning and how to actually build, right, pretty powerful models. All right, so then in the following course, this is the more advanced level course, graduate level course called General Models. And it's a special topics course. And so the course code is 983. There's like other special topics courses too, right? So if you want to enroll, you just want to make sure to check, right? If it's actually this course, it usually says in the description. So essentially in General Models, what we do is we're going to be essentially trying to predict, kind of trying to generate data, right? Rather than trying to generate labels for the data. So if we have, let's say, computer vision, for example, we would like to figure out, right, where, let's say, the person is or the bicycle is, right? In general modeling, right, what you want to do is the reverse, right? So you want to generate, let's say, an image, right, from a segmentation mask, right? In this example, or maybe, in other cases, you want to generate, let's say, color versions of grayscale images, or maybe you would want to generate different completions, right, of a 3D shape. And the way that general models do this, right, is to essentially try to model the underlying probability distribution, right? So let's say, for example, in this problem, if we're given a bunch of real data points, right, real images of cats, the goal of general models is to just generate, right, other similar examples, right, that are also cats. And the way we do that, right, is to say, well, I mean, we are going to view these different images of cats, right, as just samples from some underlying probability distribution. And now, in order to just generate new images, we are going to draw samples, right, from that same distribution, right? And so the goal here is to just infer, right, what the probability distribution is from examples of the data. And so the hard part is that we don't really know, right, what the probability distribution is, right? All we're given, right, are just a bunch of examples, right, of images. Typically here, you have like pretty complicated data, right? So the images have like lots of different, variation, right? And then you can have different kinds of objects, right? So, just actually inferring that probability distribution is pretty hard. And so in this course, we're going to go over how to actually do that. So there are three different problem settings in general modeling, right? So the simplest is unconditional general modeling, which is to model the just the marginal distribution, right, over some random variable y, right? So that could be, let's say, the image that we looked at. You can also have conditional general models, and then this is trying to model the conditional probability distribution over y given x, right? Where x is just something that you are given, right? So it could be a class label. So maybe it's a calico cat or a tabby cat, or it could be, let's say, a textual description, right? So these are all examples, right, of discrete labels. And then you have a slightly different setting where the labels are continuous, right? So you can have, for example, a scene segmentation, right? Or you can have a part of an object, right? A 3D object. And then in both of these cases, all the data is continuous, right? So you don't really expect to see the same thing more than once, right? It's like every data point would have a different value for X. Okay, now how do you actually take these courses? So the first one, right, machine learning is a cross-listed course, so that will be offered in the spring and the fall. So it's offered twice in the year. So it's pretty easy to, kind of find to take in some sense, right? It's cross-listed, right? So you can just select the course. And then the second course, the general modeling course, is a graduate level special topics course, and that will be offered in the spring. So you need to petition to take that. What that means is that you want to kind of essentially fill out the form, right, to add the course, and then you just need to get my permission to take it. So you must take the machine learning course before the graduate level general models course. And if you haven't taken for 10, right, the machine learning course, then you won't be allowed to take the second course. In terms of the background that is required, so machine learning is a very mathematical discipline, so it's pretty math intensive. So that is why, right, you need to have taken, a lot of math courses before you can take machine learning. So in particular, you need to have taken calculus, the two courses at least, right? Linear algebra, ideally 240, and probability, Python, and numerical algorithms. Another course that's highly recommended is multivariable calculus, right? So that's Math 251. So if you take that, then you'll be a lot better prepared for the course. And at the bottom, I have this resource, right, that is, pretty helpful. So it's available for free. If you go to that link, then you should be able to download that, and you can essentially get all the different kinds of math, right, that you need. So if you feel rusty on any of the math, right, just take a look at that book and review that, right? And that is pretty much it. Are there any questions? Okay, yep.
And they usually offer like drop every spring and fall. Right?
Yeah, that's right. Yeah, it's offered twice. Yeah. So I usually teach in the spring, and another professor, Dr. Mo Chen, teaches in the fall. Any other questions? Okay, all right. Then that is it. Okay, all right.
Okay. Let's see if it works. All right. So, hello everyone. I'm another instructor here to give a short guest lecture at 361. Before getting started though, I want to begin with a quick visual puzzle. I'm showing a few images here. Each of these was retrieved through search through this specific word. And the puzzle here is to guess what are the words for each image. The words correspond to a sequence of words that spell out something. Any guesses about the top left one? Any word come to mind? Yeah. Say again?
Schematic.
Schematic. Getting close. So maybe more specifically, topic in this class. Yeah. Design. Getting close. Getting close. So maybe let's give a hint. Something you learned about in this class that allows for those kinds of images to be built in. Yeah.
Rendering.
Rendering. The first word is rendering. What about the top middle?
Eye.
Eye. Other word that's related to eyes. Vision. Similar. Similar word.
Sight.
Sight. Maybe getting a little bit farther. Let's get closer back to vision. Any related words? Any guesses? Starting with a V. Very close to vision.
View.
Yeah.
Visualize.
Visual. Visual. Yeah. What about the top right? It should be getting easier now.
Code.
Code. Programming. Another word. Computing. Rendering and visual computing. Now it should be getting increasingly easier for artificial intelligence. So artificial and intelligence. So that's the title of a course I'd like to tell you a little bit about. A course that you can take after taking this intro to visual computing. So the course is called Rendering and Visual Computing for Artificial Intelligence. Before I tell you about that though, let me say a few words about myself. My name is Manolis Sava. I am an associate professor in the School of Computing Science. This is a brief summary of my academic journey. I started as an undergrad at Cornell University, went to Stanford for my PhD, and then did a postdoc at Princeton University. In between these, I spent a little bit of time interning at Square Enix in Tokyo, Japan, in their graphics R&D team, and also a bit of time at Facebook AI Research, trying to do research that connects visual computing and AI. And now I'm here at SFU to say a little bit more about the kind of research that I've done, gives a bit of a perspective on the class I will describe. Broadly, you can think of it as this topic of visual computing for modern AI. What does that mean? It means modeling, simulating these kinds of indoor spaces and other digital representations of the world so that we can run experiments to study and develop various forms of artificial intelligence that can navigate spaces, that can understand where objects are, that can manipulate those objects. That's why you see these examples here of various, robots moving around. So that's the general idea. Coming back to the class, this is the title. That's the course number, 469/722. This is typically cross-listed between undergrad and grad. And to explain what this course is about, I'll break it down by looking at the words in the title. So these are highlighted in different colors now. The first part, which says rendering and visual computing, it's generally describing things that we've learned about in this class. Algorithms, data structures, systems that we design that help us produce realistic images, or related systems that help us to acquire data from the real world that is somehow helpful in producing such images. The other part is AI, It probably doesn't need any explanation, but that is the dictionary definition there, right? Systems that are capable of performing tasks that normally require some notion of human intelligence, things like visual perception, speech recognition, decision-making, and so forth. And then the last actually important part is this course numbering. 469 and 722, what that is indicating is that this is a research-focused course. It's a course that is targeted to beginning graduate students, but also undergrads like yourselves who have taken other third year and fourth year courses as prerequisites. And one critical piece about this is that due to this research-oriented nature, the course is based on primarily looking at research papers and topics that have not yet really made their way into textbooks, into standardized materials. Now you may ask, why this particular topic, visual computing for AI, and more specifically, why is this useful, right? Why should there be a course on this? The reason is that in recent years, the kinds of methods you saw in this class to render, to produce, nice photorealistic images, and to simulate what the world looks like, these kinds of methods are being used not only for people, not only for human eyes to look at, but for a variety of systems that we want to train to do various tasks. Here you see some examples: visual navigation, robotic grasping, dexterous manipulation. These are just a few examples that have in some way used rendering to create data that is useful for training and evaluation of various, methods that do navigation, manipulation, grasping, and so forth. So that's the main reason why this focus, because nowadays it's actually useful to generate visual content not only for human eyes. Just to give a quick overview, this will be pretty rapid, but I'll try to give you the overview of some of the topics covered in this course. The first part will actually connect pretty directly to things that you saw in 361 by describing how we can model 3D shapes, the geometric representations that we use to model 3D shapes, and in particular, scenes composed of many shapes, especially when these scenes get really complicated. There's an example here on the left from the Moana movie, right? This is a tropical island, and some statistics about how many primitives, geometric primitives, are being used to represent this scene. With these numbers, 15 billion primitives total, we need to have some methods that help us manage that complexity, make it actually computationally feasible to load this up, run various rendering algorithms efficiently, and produce these kinds of images that you see here. So we'll study things like level of detail algorithms, an example of which you see on the right here, that allow us to take something that is geometrically complex and then perhaps progressively produce versions of it that are more and more simplified, that use fewer and fewer primitives to represent that same object. You see there an example of an airplane being progressively simplified, and we're producing in this way various levels of detail of that airplane. So this is the first part, which is focused on modeling of complex scenes. After this, the class will focus on introducing some more advanced rendering fundamentals. You saw in this class, rasterization and ray tracing, but to go a little bit deeper into what's called physically based rendering that is based on the principles of physics and how light, is transported through scenes. We'll study a little bit more about concepts coming from radiometry and photometry, from physics itself, and we'll connect these concepts to what we do in rendering. And in particular, we'll explain how these concepts led to the definition of representations such as light fields, radiance, and so forth. The visual that you see there is this experimental setup that was designed to capture so-called light fields, the total appearance of an object from all points of view in a particular scene. Once we cover these fundamentals, we'll then study more advanced physically based rendering algorithms, particularly extensions of the basic ray tracing algorithms you saw in this class. Extensions that are called path tracing and volume rendering, where we can now see or represent how light interacts with complex participating media, examples of which you see here on the left. Things like clouds, smoke, even human skin. Human skin is a fairly complex material that interacts in a complicated way with light. We'll formulate this mathematically. We'll derive some equations that help us to design algorithms that tell us how light propagates through these kinds of materials so that we can produce those kinds of images. After that, we'll turn things around a little bit and discuss how rendering algorithms can be made differentiable and how we can invert the rendering pipeline. Differentiability is a property that is pretty useful nowadays, especially when we want to combine traditional rendering with machine learning and with this goal of using visual computing and rendering for artificial intelligence. So being able to differentiate and compute how a particular part of the output image depends on parameters, right? What is the connection between those two helps us to establish a pipeline that we can then use to take an image and estimate what are the parameters that produce that image. So the example that you see here on the right is showing some images of fruit, some pears here, and a inverse rendering pipeline that progressively estimates what the geometry of this fruit is and what the materials of the fruit are, so that we can then essentially acquire the model that produces the image. That's the general idea. Can we, from an image from the real world, create a model, create the materials? The continuation of this is to look at so-called neural rendering. Now we're introducing various neural architectures in our rendering algorithms. One of the most well-known variations of this is called neural fields. You see that on the top left there, neural fields that allow us with a neural network to represent a volume, essentially. What exists, how does an object exist in a volume? What is its appearance? And on the right, we see some nice animations that again show examples of results from neural rendering approaches. After this, the course focuses on synthetic visual data generation, which is really one of the those motivations that I described at the beginning. Various tasks that benefit from generating lots and lots of visual data using rendering algorithms. There's here an example of a research paper that studies this, and then we'll discuss in detail why this is becoming very popular in recent years. In the last 5-10 years or so, and into the future, why is synthetic visual data generation so popular? And we'll talk actually in more detail about specifically generation of 3D content, why that is still challenging, and in particular, why it's important to try to do it algorithmically. What are the ways in which we can help people design 3D content more efficiently? the challenges that we're trying to resolve algorithmically, and how we can connect, these algorithms with people who design the content. And towards the end, the class will focus on so-called high-performance graphics for embodied AI. This is, taking this generation of visual data, synthetic visual data, or 3D content that is used to produce visual data, and really trying to make it efficient, trying to make it scale well so that even with, let's say commodity GPUs, devices that you can, that any user can have, we get high enough rendering speeds that experiments relying on lots and lots of visual data are unblocked. Here you see an example of a scene, pretty high quality, near photorealistic scene being rendered from one of these high performance graphic systems targeted specifically to embodied AI. And the point that this part of the course is making is that once we have this new way that we want to use rendering, which is no longer about humans, it's not humans that are looking at images that are being produced. There may be different design decisions that we might want to make in terms of how we run our rendering algorithms, how we stage, rendering on graphics hardware so that it becomes more efficient and better at producing especially various modalities. In addition to just images, things like distance from our current viewpoint, so-called depth, right? Depth maps, other simulated sensors like LiDAR sensors, some of you may have heard of. So doing this efficiently and concurrently is the focus of this part of the class. So that's pretty much it in terms of the very quick overview of the topics covered in the course. I mentioned earlier that a lot of the topics have not yet made their way into textbooks, but one part that has is the physically based rendering part, more advanced algorithms that are based on principles from physics. This is the textbook that we will rely on for that part of the class, the earlier half. And this textbook is actually famous or infamous for an interesting reason. This book led to an Academy Award for the authors, Academy Award being an Oscar, a so-called technical Oscar, because on the basis of this book, much of what is being done nowadays in the visual effects industry for movies has been developed. The quote that you see there is from a well-known computer scientist saying that, Donald Knuth, he believes that the book is deserving of this Academy Award, and he thinks that it should be even more recognized because it's so well written. So this is the book that we'll depend on. But as I mentioned, for a large part of the class, for most of the latter half, we'll really be looking at research papers. And here you see some screenshots from a set of papers in the most recent version of the class that we'll look at together, read through, summarize, and then discuss. To give you a general idea of how the class is structured, well, firstly, it has as a prerequisite this course, the one that you've been taking, 361, as well as 410, machine learning. I think you heard about 410 just before this, right? So both of these are required because, as you said at the beginning, this is a course that combines the two sides. It combines visual computing with machine learning and with AI. So these are the two prerequisites. And in terms of the structure of the evaluation, it's split roughly into three key components, 30% or so on reading the research papers and critiquing them, another 30% on presenting on these papers in class, discussing them in class. And then lastly, the biggest component is a self-selected project done in groups. It's a project where, as a group, you pick a topic of interest, you dive deeper into that, you try to implement something, a cool system maybe that renders some unique visual phenomenon or an efficient way to render for embodied AI and so forth. So that's pretty much everything. If this seems interesting, consider enrolling in the next available offering of 469,722. Typically, it's offered in the spring. If you're more generally interested in these kinds of topics, or you want to learn more about, the details of what's covered, and if there are other related, courses that might be interesting, feel free to get in touch. My email is there. And also consider getting involved in research. The course that you took here at 361 gives you some of the fundamentals that unlock many interesting, research projects that a lot of the visual computing faculty members here are doing. So not just me, take a look at all of the visual computing faculty at SFU in computing science, see what kinds of research projects they're doing. If anything seems interesting to you, I would strongly encourage you to get in touch and ask if there are opportunities to get involved with research. And that's all. I'm happy to take any questions if anybody's interested in learning more about anything specifically. Yeah.
You mentioned it was offered spring.
Yes.
Is it everything?
It's typically every spring, though probably not the next spring, unfortunately, because I will be away on sabbatical. So not for a while, for a year and a half. Any other questions? Oh, yes.
You mentioned path tracing. How does that sort of differ from traditional English response?
Right. Yeah. So if we go back to this diagram that had the path tracing, with ray tracing, you typically don't have to consider complex paths that light takes through the scene. Paths that involve things like, participating media, interactions in the volume, or, where the way that light gets distributed through a material is not a simple reflection. So that's really the key difference between, the ray tracing, the first introduction to ray tracing that you saw in this class, which is mainly concerned about reflecting off of surfaces, and path tracing, where we really start to consider much more complex paths through, various materials in the real world, like, skin and so forth. Anything else? Yeah. Oh, sorry. I thought that was a hand. Yeah. Yes.
Aside from prerequisites, is there any kind of recommended background or anything to?
Yeah. Yeah, it's good to have taken, well, as you see, there are some partial derivatives here. So multivariate calculus is a good idea. So Calc 3, I would strongly recommend. Yes.
How much the whole course then is more towards multivariate calculus physics versus the data driven ML? What's the split in it?
It's roughly half and half, roughly. Yeah. So as you saw in this kind of overview, right? It's rendering fundamentals, path tracing, volume rendering, differentiable inverse rendering, and then it gets into neural rendering. So roughly, at this halfway point, it's where it starts to switch into more, neural architectures and data-driven methods.
How old are the data-driven methods? Are they relatively new or no?
We go from roughly, let's say, 15 years ago up to within the last 2 years. So as I mentioned, that's why we look at research papers, right? Much of the more recent work has, of course, not really made its way into standardized materials like textbooks. Any other questions? Thank you. All right. Yeah. Thanks. That's good. Yeah, of course. Does this so exit soon?
Okay. Hopefully those guest lectures give you some idea of the high-level visual computing courses that you can take after this class. So those are just a few small samples of the different variety of visual computing topics that are offered at SFU. And if you're interested, you could go through some of the fourth level courses to see some of the other topics that we offer in this field. For the remaining half of this class, I'm going to start by going over some of the logistics for the final exam, and then we're going to wrap up with a lecture on shader programming, which will be the final component that you need for completing assignment 4. Good. The final exam is going to be on April 23rd, 3:30 to 6:30. It's going to be held in WMC 3520. And for the purposes of this exam, it's going to be completely closed book, which means no cheat sheets, no devices. You shouldn't need calculators. All you should need would just be a pencil and a pen. There will be no complex calculations. Any calculation that will be involved can be done fairly quickly with just a pen or pencil. Now, in terms of the content of the exam, about 25% of the points will be allocated for computer vision topics. And this is going to be cumulative. So all of the material starting from the very beginning of the semester, any material that's covered in the midterm, any computer vision topics that were not covered in the midterm are all fair game. And then the remaining 75% of the exam will be on computer graphics. So all the topics that we have covered after the midterm. For computer graphics, the focus will be primarily on modeling and rendering. We didn't have enough time to go into animation, so there will be no topics on animation in the final exam. So for preparing for your final exam, you can focus mainly on the geometric modeling and rendering lectures. In terms of the format of the questions, it will be a combination of multiple choice questions, some short answer questions, and there might be a little bit of pseudocode, but nothing very complex. And all the questions will be drawing from materials from the lecture and the assignments. There are topics in the textbook that's not covered in the lectures, in which case you won't have to worry about that for the exam. Everything is going to be drawn from what we've covered during the live lectures. I guess there's been some questions about whether or not practice exams are available. Unfortunately, we don't have a practice exam prep, so we won't be able to share that with you. But if you go through the lecture materials and you go through the assignments and you're comfortable with that material, I think you should be in good shape for the final exam. Any questions about the final exam? Oh, right. One thing I forgot to mention, there's one topic that we didn't get to cover during the live lectures, which are transformations, which is part of your assignment 4. So even though we didn't get a chance to cover them during the live lectures, please take a little bit of time to watch the video lectures on transformations, and that will help you on assignment 4. And I will guarantee you that there will be questions on transformations on the final exam. So yeah, so make sure you go over that material. Okay, any questions about the final? Oh, sure, yep.
On the website, there's study material plus the slides are different.
The slides are a little bit different, but the material that we cover are pretty much identical. So you can use the video lectures as some additional supplementary material for your study. Okay, then as a little reminder, your final assignment 4, will be due a bit before the final exam on April 15th. You should have pretty much everything that you need to finish the assignment at this point. There's going to be a little bit on shader programming that we're going to cover in this class, but otherwise, you should more or less be able to complete this. So if there's no other questions about this, let's move on to shaders. So in this lecture, we're going to give you a very quick overview of GPUs and shader programming. Okay. As we discussed in a lot of the rendering lectures, the process of rendering an image can be quite computationally expensive. We have to perform a lot of different geometric transformations, a lot of lighting calculations, and a lot of shading operations. And all of these operations can take a lot of compute. So for performance-intensive applications of computer graphics, like let's say real-time rendering for games, a lot of these real-time applications are made possible using dedicated hardware that's specifically designed to accelerate rendering operations so that we can render images extremely quickly at 30 or 60 frames per second. And the key technology that enables these real-time applications of computer graphics is the graphics processing unit, or GPUs. So on the left, we have an example of one of the first GPU that was ever created from the 3dFX Voodoo, all the way back in 1996. So these early versions of GPUs are very specialized computer chips that are designed with circuits that are specifically dedicated for performing computer graphics operations. These early GPUs have a fixed set of a handful of fixed functions. So these circuits are specifically designed to perform a very narrow set of operations for making rendering operations very fast. So with these early versions of GPU, they run at about 50 megahertz, and they have a measly 8 megabytes of VRAM. Now, we can compare these early versions of GPU with more modern GPUs like the RTX 3090. And with these modern GPUs, they have over 10,000 programmable CUDA cores, which means that the circuits on these chips are no longer designed specifically for a small set of fixed function operations. Instead, they can be programmed to perform more general calculations for applications that go beyond computer graphics. So for a modern GPU like this, they can run at 1600 megahertz, and they have 24 gigabytes of VRAM. And in fact, if you look at the performance of these GPUs, it's actually comparable to a supercomputer back in 2005. So you can kind of buy one of these chips, stick it in your desktop, and you kind of have your equivalent of a mini supercomputer on your desktop. And the large amount of compute capabilities that are provided by these GPUs are what makes a lot of modern real-time computer graphics possible. So most of these GPUs are designed specifically to optimize common computer graphics workloads. And in particular, these chips are designed to be able to take a virtual scene, a mesh of objects in a scene, parameters of the camera, lighting sources, and then be able to very quickly generate realistic looking images of those scenes. And as we mentioned in the earlier rendering lectures, for a lot of real-time rendering applications, these systems tend to leverage rasterization rather than ray tracing. One of the advantages of the rasterization pipeline is that it can be fairly efficient. We can render fairly complex scenes very quickly using rasterization compared to ray tracing, which tends to be better suited for offline applications. So GPUs have traditionally been designed to try to accelerate the different stages of this rasterization pipeline. And one of the key insights that allow GPUs to accelerate rasterization is that many of the common operations that we have to perform when we are rasterizing an image, many of these operations are embarrassingly parallel. For example, when we rasterize triangles, A single mesh can have many triangles, but we can rasterize all of those triangles in parallel. For each of these triangles, we might have to perform inside and outside tests. But those inside and outside tests can be performed independently for each triangle in parallel. Similarly, for operations like barocentric interpolation, evaluating lighting models, or texture mapping, all of these operations can be more or less performed independently for triangles or independently for pixels. Which means that even though we have to perform a lot of operations in order to render an image of a scene, all of those operations can be performed largely in parallel. And this is the key insight that GPUs leverage in order to massively accelerate rasterization pipelines. Another key insight that these GPUs leverage to speed up computer graphics applications is that most of the common operations that we need to perform in computer graphics are linear algebra operations. So when we are applying transformation matrices to convert objects between different coordinates, when we are evaluating lighting models, when we are performing inside and outside tests for rasterizing triangles, all of these operations are largely linear algebra operations, which means that if we can design special hardware that's specifically dedicated to accelerating linear algebra, then this can automatically allow us to speed up many of the operations that we need to perform when rasterizing an image. So these are the characteristics of a rasterization pipeline that GPUs will use in order to make rendering extremely fast. Any questions about this?
Is that why GPUs tend to have more cores than CPUs?
Yep, exactly. So because GPUs have to perform so many operations in parallel, the way that they do this is by having just physically lots of cores on the chip that can perform lots of calculations in parallel. Question?
About like tensor processing.
Yeah, so tensor processing units are, in principle, they leverage a lot of the similar principles as GPUs, but rather than being maybe designed to support computer graphics units, those tensor processing units are a bit more specifically designed for, let's say, machine learning operations. But again, they leverage a lot of these parallelism that's inherent in these machine applications, similar to computer graphics. And it's because of the similarity, like the parallelism that's inherent in both computer graphics workload and machine learning workloads, that GPUs have also become extremely useful for applications in machine learning that have nothing to do with computer graphics. So for a lot of machine learning applications, we have to perform lots of linear algebra operations in parallel, which is exactly the type of workloads that many of these GPUs are specifically designed for. Right. So if you look at a schematic diagram of one of these GPUs, what you see on the surface of these chips is that there are many blocks of compute cores that are repeated over the surface of the chip. And if we zoom into each one of these little compute units, what we'll see is that they have dedicated circuits that are specifically designed for linear algebra floating point operations. So by having many of these small compute cores repeated over the chip, these GPUs can leverage these small cores to perform lots and lots of calculations in parallel. So this is a physical implementation of the massively parallel workloads that we see in computer graphics. Okay, so now let's take a look at how we program these GPUs in order to render images. Many of these rasterization pipelines are implemented on a GPU as a series of stages that roughly correspond to the different stages of the rasterization pipeline that we discussed earlier. Each one of these stages are carried out by small programs referred to as shaders. And these small programs are written to carry out a specific task in a massively parallel manner. So starting at the top of the stack, we might have an application. This would be, let's say, an app that you write in C++ or Python, which is going to set up the virtual scene that you want to draw with your GPU. So this application might construct the vertices of all the objects in the scene, all the lighting parameters, the camera, and then it's going to send that information to the GPU. The scene will generally be represented as a large cloud of vertices that form a mesh. And these vertices are going to be first processed by a vertex shader. The job of this vertex shader is to apply per vertex calculations on the vertices produced by the application. So for example, if I have defined lots of objects in row space, and now I want to render the scene from the perspective of the camera, one of the operations that you have to perform is to take all those vertices from row coordinates and convert them into camera coordinates so that we can display the scene from the perspective of the camera. And so the vertex shader's job is to take the input vertices, apply transformations to those vertices, like converting the vertices between different coordinate frames, and then outputting a stream of transformed vertices to the later stages of the rasterization pipe. After the vertex shader, the vertices that's produced by the vertex shader will be processed by some additional stages of the pipeline. And then at some point, it's going to arrive at another key stage of the GPU pipeline, which is the fragment shader, or sometimes referred to as the pixel shader. The job of the pixel shader is to perform shading calculations on the pixels that we are drawing on the image. So given the vertices produced by the vertex shader, we are going to project all those triangles onto the image plane. We are going to figure out which pixels are covered by the triangle. And then for each one of those pixels, we are going to apply the fragment shader to calculate the color that we should assign that particular pixel. And this fragment shader can be applied in parallel to all of the pixels that we're currently trying to shade in. And then at the very end, the output of the fragment shader will be a color that will be stored in the frame buffer that we eventually show on screen. These shaders are typically programmed using some C-like languages like HLSL and GLSL. And for your assignment 4, we are going to ask you to implement some simple shaders in GLSL. So to help you with that, we're going to go through a quick demo of how to program some of these shaders. So for this shader demo, we're going to use this app available at this link here. So if you want to follow along, feel free to kind of to go to that link. So just to give a quick intro of how the shader app works. So this is a simple app that allows you to kind of play around with different vertex and fragment shaders. So on the left, we have the editor. You can pick between either the vertex shader or the fragment shader. And then on the right, you have a mesh that's been rendered using the vertex shader and the fragment shader that's written in the editor. Right. So here we have a little monkey model, but you can also pick between different models as well. So for example, you can pick a simple cube. You can use a sphere, and you can even pick something more interesting like the Stanford Dragon. So and you can use these different meshes to test out your shaders. Now to start, let's take a look at the vertex shader. So the job of the vertex shader is that your application is going to send a stream of vertices that represent the meshes in the scene. And the vertex shader is going to apply some transformations to those vertices in order to rasterize the image. And this vertex shader is a very small program that's going to be applied in parallel to all of the vertices that we are drawing. Now, this particular shader is implemented using GLSL. I want to go over some of the different data types that you're working with when writing these shaders. Okay, so first, there are different types of variables that act as the input and the output of a shader. Okay, so first we have, these varying variables. Oh wait, so no, not good. Sorry. First we have these attributes. These attribute variables represents the inputs to the vertex shader. So these attributes represents different types of information that we store at each of the vertices of our mesh. So for example, for every vertex, in this example, we store the position of the vertex as well as the normal vector for that vertex. But for more complex applications, you can store other informations in the vertices as well. You can store vertex colors or texture coordinates, anything you want. And those will be fed in to the vertex shader as these attribute variables. Besides the attribute variables, we have uniform variables. These represent variables that are shared across all vertices. Attributes are the quantities that are specific for each individual vertex that can be different from vertex to vertex. Uniform variables are going to be constant, the same across all vertices. So all of the vertices that we are going to draw is going to share the same uniform variables. And these uniform variables are used to represent things that do not change in the scene. Things like the camera transformation or the projection transformation. These are things that are determined by the camera, and the configuration of the scene, and they're not dependent on the vertices themselves. And then finally, for the vertex shader, we have these varying variables, and they represent the outputs of the vertex shader. So any information that we store in these varying variables will be outputted by the vertex shader and sent to the later stages of the GPU pipeline. Okay. So any questions about these input and output variables? Yep. Yep. Right. So let's go over some of these different transformation matrices. Let's start with the model view matrix. The model view matrix is a matrix that's used to convert from model coordinates to the camera's view coordinates. So when you create a mesh, it might be defined in some coordinate system that maybe your artist used to create that model. But if you want to render that object from the perspective of the camera, we have to convert that coordinate to the camera's coordinate system. This view matrix is a transformation matrix that transforms vertices from the initial model coordinates to the camera's coordinates. Now, after that, we have this projection matrix. And the job of the projection matrix is to take vertices that are defined in the camera's coordinate frame and then project them onto the image plane. And the normal matrix, it's kind of like the camera view matrix, but it's the transformation matrix that we need to rotate normals from model coordinates to camera coordinates. So, oh, sorry, no, right. So, it's just taking a matrix and then multiplying a normal vector by that matrix. So it just converts it from one coordinate frame to another. No, they're separate things. Model view matrix is used to transform the positions. The normal matrix is used to transform the normals. They're pretty much the same transformation, except that the normal matrix don't have translations because that would kind of incorrectly modify your normal vectors. Now, in addition to these output varying variables, there's one special output variable in the vertex shader, which is this GL position variable. And this is going to be the output of the transformed vertex positions after they have been projected onto the image plane. So these are the positions of the vertices after they have been projected onto the image plane, and we assign them to this special GL position variable in order to be passed on to the later stages of the pipeline, like the fragment shader, to actually rasterize that triangle onto our image. In addition to these different types of variables, there are also these different data structures that we use in order to perform a lot of these rendering operations. A common data structure is the vectors. So vec3 is the data structure that we can use to specify a 3D vector. So for example, I can specify a 3D vector like this, 0, 0, 0, 1, and this will give me a 3D vector that has components 0, 0, 1. You can specify a 4D vector as well with vec4. So here, this will give you a 4D vector instead.
My 10 and 11, what's the F or F normal?
Yeah, so these are just the output variables, and F here just specifies that these are going to be the quantities that will be passed to the fragment shader later. So the positions and normals here will eventually be passed to a fragment shader for the lighting calculations.
So they're like position and normal attributes after.
Yep, that's right. All right, so if we look at F position here, this F position takes the input position from whatever application was written. It multiplies that position by the model view transformation to transform into camera coordinates. And then we assign that 3D position to the output F position variable. Okay. So now I'm going to define, let's say, right, so we can use the vertex shader to apply different transformations to our vertices. So for example, I can define a new position, which is going to be the O position. And I'm just going to replace that O position with this new position. Okay, nothing has changed, but we can apply some different transformations to this position. For example, if I scale the X coordinate by X, that squishes my dragon a little bit. So now it's a little bit thinner than it was before. I can multiply this by 2, and this will stretch. Oh, yep. And this will then stretch my dragon. to be a bit taller. We can apply more complex transformations in the vertex shader as well. For example, we can define a transformation matrix using the data structure map3. This is going to define a 3x3 transformation matrix. Now, one thing to note about GLSL when specifying matrices is that it uses a column major format, which means that we specify the elements of a matrix one column at a time. So here, 1, 0, 0 is not corresponds to the first column of the matrix. It's not the first row. So you need to be careful about that. The way that we write out the matrix is kind of transposed compared to how that matrix is actually stored. Okay, so this is now I can take this matrix and I can multiply my new position by this matrix. Right now, it's not that interesting because it's just an identity matrix. It doesn't change the vertices at all. But I can modify the elements of this matrix in order to transform my vertices. So for example, if I make one of the elements negative, I can flip my dragon the other way around. If I make one of these elements smaller, I can squish my dragon. And then if we modify this matrix a little bit, I can rotate my dragon by 90 degrees. So by specifying different matrices in the vertex shader, we can apply some fairly complex transformations. Now, to go as a slightly more extreme example of what you can do in a vertex shader. We can do some simple animation in the vertex shader as well. First, I'm going to define a new uniform variable called time. This is a special variable that the app defined to specifically represent the time. This is something that's not generally built in. If you're developing your own rendering application, this is something that you have to feed in to the shader from your application. But here, this is time variable is built in, so this is going to give us time. And we could then use this to modify the position of the vertices. So let's say I'm going to modify the x component of the vertices based on time, and then I'm just going to write some random function here. So this is going to apply some sinusoidal offsets to the vertices based on time. And then we'll get something like this where we can get the dragon to wave a little bit. Okay, yeah. So by kind of writing more fancy and fancy vertex shaders, you can create some pretty interesting effects. And again, this vertex shader is some simple little program that's going to be applied to every single vertex that we are drawing. Any questions about this vertex shading? I think we don't have that much time left. Okay, then oh, sorry, what? Oh, you shouldn't have to import the cosine function. It should be built in. Did you spell it wrong? Oh, we're on the exact same website. Oh, okay, that's strange. Oh, yeah, sorry, my question was what? Okay, but you won't need the cosine for the rest of the demo. So that's a vertex shader. Let's go to the fragment shader. Okay, so the fragment shader is similar to the vertex shader, but instead of being applied to every single vertex, the fragment shader is going to be applied to every single pixel that we are drawing in our image. Similar to the vertex shader, the fragment shader is going to have different input variables. Uniform variables, again, are things that are shared for every single pixel. They're constant. Varying variables, on the other hand, are going to be the inputs to the fragment shader. These varying variables are the outputs of the vertex shader that's been sent over to the fragment shader. So F position and F normal, these represents whatever positions and normals that are being outputted by the vertex shader. The output of the fragment shader is going to be this single special variable called GL_FRAG color. And this is going to represent the final color that we assign that particular pixel that we are drawing. So for example, here right now, the color is being assigned to the normal vector is being used as a color, which is what gives us kind of this particular appearance for the dragon. But we can change the color however we want. So for example, if I want a green dragon, I can specify 010, and then that will make my dragon green. So this is saying that every pixel that I'm drawing, I'm going to assign the same green color to that pixel. Okay. So let's just define a new variable called color. This is going to be a 3D vector. And you can make it any color we want. Well, in this case, it's just going to change the dragon to red. And we can perform more complex lighting calculations in the pixel shader as well. So let's do something a little bit trickier. Okay. Now, in this case, I'm going to apply some transformations to my normal vector, and then that can give you kind of a psychedelic looking dragon. Okay. So, oh no, the normal is not a color. The normal is just a vector that tells you what the surface direction is. But then it's a 3D vector, so we can visualize that as a color. Of the triangles, yep, that's right. No, sorry, right. The normal vector is defined at the vertices, but when we color in the pixels of the triangle, we're going to interpolate the normals at the vertices to get a point in the inside of a triangle. Yeah, so all the points inside the triangle, they might have slightly different vectors, and the normal vectors are determined by barycentric interpolation of the normal vectors that's defined on the vertices. Okay. But, yep.
Can you explain what's the 1.1?
Oh, sorry, what's the what?
So we have GL_FRAG color equals vector 40 vector.
Yep.
Color.
This represents an alpha. So unfortunately, this is not, I don't think this is really being used, but alpha can be something that you use for kind of like transparent objects if you want something to kind of be see-through.
Oh, so it's just expanding that big vector.
Yeah, that's right.
And then
Yeah, just adding an extra one at the end. Because GL_FRAG color is going to take RGB and then alpha. Okay. So 1 sec. Oh, oops. Wait, what? I did mine. Okay. Okay, then let's go through some examples of slightly more sophisticated things that we can do with fragment shader. Right, so let's define a new color. And I'll just make it white for now. Now, let's go through an example of how we might implement different shading models. Like the Lambert model. For the Lambert diffuse model, we need to define a few quantities first. So first, we need to define the configuration of the light. To keep things simple, I'm just going to hard code a directional light inside a shader. So normally, this light might be something that you have to pass in as a uniform variable. So it's going to be something that's specified by the scene. In this case, I'm just going to hard code it inside a shader. So here I have defined a 3D vector. Because the light direction has to be normalized, we're going to normalize the 3D vector. Now, next, we're going to define the color of the light. And for this, we'll just go with a plain white light. Next, in addition to defining the characteristics of the light, we also have to define some properties of the material that the object is made of. So in particular, we need to define the albedo, which is the surface reflectance of our object. And for now, let's just set it all to way to keep it simple. Now, with all these quantities, we now have everything we need to implement the Lambertian diffuse model. The key component of the Lambertian model is going to be a dot product between the normal vector and the light vector. So in this case, I can take the input normal from the vertex shader. I can use this built-in dot function to compute a dot product between the normal vector and the light direction vector. And this would then give us the cosine between those two vectors. Next, because the dot product can be negative, we need to clamp that dot product. So we can take a max of 0 in the dot product, and that would just clamp all of the negative values. And finally, we can then put all this together into the Lambertian model, where we take the dot product, we multiply it by the albedo of the surface, and then we also multiply that by the color of the light. So this now gives us the color for the diffuse model. And if we replace the output color with this particular color, you'll get something that looks like this. So now the light is roughly coming from somewhere in this direction. So, oh wait, well, I guess it's coming from this direction instead. So any surface that's pointing towards the light end up being brighter, and then surfaces that are pointing away from the light will look darker. We can change the color of the light. So if I want a red light, then this is going to make my dragon look red. If I change the albedo of the surface, then I can also change the color of the object. So in this case, I have a green dragon instead. Any questions about this Lambertian model? Okay, so very simple model. You can implement it in just a few lines of code. But the thing to note is that the Lambertian model is mainly designed to render surfaces that are very rough, that will reflect light more or less uniformly back out into the scene in all directions. So looking at this dragon here, looks like it's made of maybe some rough material, maybe like concrete or rock. But let's say we don't want a rough dragon. I want a shiny dragon that looks like it's made of metal. Then to do this, we need to implement a slightly more sophisticated lighting model. So next, let's take a look at how we can implement the Phong lighting model. Now, for the Phong lighting model, we need to define one additional parameter, which is the shininess value. This is kind of an arbitrary value that we can pick to start. Let's just go with 20, just some arbitrary value. To implement the Phong model, we have to, again, calculate a dot product, but it's going to be a slightly different dot product. For the Phong model, we are trying to model what mirror-like reflections look like on a particular surface. So to do this, we need to calculate the reflection vector. Now, luckily, GLSL has a built-in reflect function that allows us to take the light direction and reflect it along the normal vector. So this function will just take a vector and then reflect it along a different vector. Now, here's one detail that you need to be careful of. And that is that the light direction is not the direction that the light is traveling in. It's the opposite direction that the light is traveling in. So the light vector points from the surface to the light, not from the light to the surface. But if we want to calculate the reflection vector, we need to reflect the vector that corresponds to the incident direction of light. So to do this, we need to take the negative of the light direction and then reflect that to get our reflection vector. So this is a common bug on assignment 4, so make sure you be careful of that. For the Phong model, we compute a dot product between the reflection vector and the view vector. And the view vector corresponds to the direction from the point that I'm trying to color in, pointing towards the direction of the camera. Okay, but now how do I get this view direction? Where do I get the camera position from? It's not necessarily passed in explicitly as any one of these variables. So the way that we can find the view vector, the camera direction, is by taking the position from the vertex shader. So the vertex shader takes vertices defined in some coordinate system, and then it transforms those vertices to the camera's coordinate system, which means that the positions that we have from the vertex shader are positions with respect to the camera. So now, if I know the position of the point that I'm trying to color in with respect to the camera, then if I want the direction from the point to the camera, this corresponds to just normalizing the position, and then taking the negative of that. So the position corresponds to what is the difference in position from the camera to the particular point. So if I want a vector pointing from the point to the camera, that just corresponds to the normalizing the position and taking the opposite direction. So now we have the reflection vector, we have the view vector, and this gives us everything that we need to implement the Phong model. So we're going to take a dot product between the reflection vector and the view vector. And again, we can use the built-in dot function. Again, this dot product can be negative, so we need to clamp all of the negative values to 0. Oh, right, clamp's not the phone. After this, we can then calculate the color for the specular model using the clamp. Using the clamp dot product. And then we are going to multiply this by the light color. Oh, right. So we take the clamp dot product, we raise that to the power of this shininess coefficient. and then we multiply that by the light color. This gives us the component from the specular model. And then we can just simply combine it with the diffuse model to oh, so this is a vector. This is a 3D vector. Okay, sorry. Okay, so this was without specular. And then if we add a specular highlight, we get some shiny highlights here. Maybe to make this a little bit more obvious, let's reduce the albedo color a little bit. So I make the dragon darker, and now we can see the highlights that make the dragon look like it's made of some sort of shiny material. If I reduce the shininess value, that's going to make the specular highlights more diffuse, which makes the surface look a little bit rougher, a little bit less smooth. And if I increase the shininess value, this will make the highlight sharper and make the surface look shinier. Okay. So these are some simple examples of how you can program a shader, and you can do some pretty wacky things in these shaders. So part of your assignment 4 will be to implement some of these shaders, and you can more or less follow kind of the procedure that we took in this example. Okay. Any questions about this? Okay. Right. This is mainly everything that I wanted to cover for today. Any final questions before we wrap up? No.
When we're planning, we're shooting between 0 or the dot product. Is it possible we can have?
So what?
So we have done 2 assignments, one online between they're both max and 0 or the dot.
Yep.
Products.
Yep.
Is negative value possible to be?
Yeah, it's possible to begin with. So for the let's say for the Lambert model, if the angle between the light direction and the normal vector is greater than 90 degrees, then this dot product can be negative. And similarly, if the angle between the reflection vector and the view vector is greater than 90 degrees, then the specular component can also be negative. There's a question in the chat about whether or not G2 on reflections and shadow mapping will be on the exam. We didn't have enough time to cover that lecture, so that won't be on the exam. The only topic that will be on the exam that we didn't get around to covering will be on transformations, which you need for assignment 4. So please watch that video lecture. Okay, any other questions? Okay, if nothing else, just a quick reminder about course surveys. All of you should have received a link requesting you to fill a course survey. Please do take a few minutes to fill that out. SFU takes those surveys quite seriously. So it would be appreciated if you can take some time to provide some feedback for this course. Okay, if not, otherwise, yeah, good luck preparing for your final exam.
Sorry, I couldn't attend the first half in person. I watched some of it
Oh, yep.
through Zoom because I had to go to the other two as well. So they were the only